Assalamu alaikum, welcome to Yasmina Shanan Physics Online course for grade 10 students at Dakahlia School. Completing Thermodynamics of lesson 3, we will talk about specific and latent heat. What will be covered in this lesson? Heat capacity, specific heat capacity, latent heat, specific latent heat, and their types of latent heat of fusion, latent heat of vaporization, and finally latent heat of sublimation. Specific heat capacity. How much heat energy is something you can store? If I asked you these questions, how come you can answer this question? If we have a smaller object and another one which has a higher mass than this one, which one of them can store more energy, first one or the second one? Let's show what are the main properties that something will store energy of. The first property, which is a type of substance. If we have two containers, the first one has a graphene and second one has water. By adding a source of heat as the flame here, the temperature of the change in temperature of graphene will the change in temperature of paraffin will be higher than that of water, as according to the specific heat capacity which is found in water, which causes a smaller heat capacity for paraffin than that of water. Okay, this is the first factor. The second factor, which is the mass of the substance. The second factor is the mass of substance. If we have container of smaller mass than the others, then the change in temperature of the smaller mass will be higher than that of the smaller one. So the temperature rises depends on its mass. Third factor, which is the amount of heat supplied. If we have a container and another one and of the same mass, and we added here a thermal source of heat for 1 minute and this one for 5 minutes, then there will be an increase in the amount of heat supplied will be larger heat, so the temperature rises depends on the amount of the heat supplied. So we can collect all these variables as the change in temperature has a direct relation with quantity of heat and the inverse relation with mass and the specific heat of the substance. And there's the proportion here as we showed in the three substances. Here there is a direct relation here with the change in temperature, inverse relations in the amount and the type of the substance. Okay, so we can define the heat capacity as it's the amount of heat expressed in calories or kilocalories or joules needed to raise the system's temperature by 1 degree, expressed in Kelvin or degree Celsius. Okay, so we can put a definition for this value, put the formula for this quantity as the heat capacity equal to Q over delta T, as there is a direct relation with the quantity of heat and an inverse relation with the change in temperature, and its unit is joule per degree Celsius. Specific heat capacity, it's specific for some type of substance, so it can be defined as the amount of heat needed to increase the temperature of 1 gram of a substance by 1 degree. Shown here, specific heat capacity has a direct relation with the quantity of heat and an inverse relation with the mass of the substance and change in temperature. Okay, its unit is joule per gram per times degree Celsius. Shown the specific heat capacity for lead to be 0.125 or 0.25 joule of heat required, as this value of quantity of heat required to raise the amount of 1 gram of lead by 1 degree Celsius. Okay, you can see that this quantity is a specific heat capacity. Molar heat capacity, the amount of heat needed to increase the amount of 1 mole of the substance by 1 degree Celsius. It can be defined, expressed its unit by joule per mole times degree Celsius. For example, if we could say that the mole heat capacity of lead this value, so that means that it takes this amount of joules of heat to raise 1 mole of lead by 1 degree Celsius. Let's show how to determine specific heat capacity for different metals by this experiment. We have 3 different metals here. We must use a distilled water to measure the exchange of the molecules. Firstly, we take pair of styrofoams to ensure that they are isolated from to act as a calorimeter, to be isolated from the surrounding, to ensure that the amount of heat transferred cannot be wasted as a wasted thermal energy into the container, and taking the weight of this container and then putting the distilled water about of 100 millimeter and taking the uh, weight of the speaker and the test tube inside to can collect the weight of the empty container here, and then we put the copper metal here and then putting it inside the test tube and taking the total mass. Then we can get the mass of this cover by subtracting the mass of the test tube and the beaker from the mass of the total amount. Okay, so the mass of this cover lead cover can be determined. Okay, then we put this test tube into the amount of water that we have weighted before, and then this cover metals will be increased in temperature, put it into a source of heat by raising the temperature of the system, and then taking this leads and putting it into the styrofoam cups and taking the final temperature of this container. Then we do the same experiment for another metals, and by substituting in the previous relation here, as we mentioned before, as the specific heat capacity equals the quantity of heat times quantity of heat over the mass times change of temperature. We have the final temperature and the initial one, and the mass of the leads or other copper or other metals, and the quantity of heat is known, so we can calculate the value of the specific heat capacity for any metal, which is specific for the same material. As shown in this graph, here is the various value for different specific heat capacity. For aluminum is 900, for copper is smaller than that, and so on. As we shown here, the specific heat capacity for water has a very large value. So, and water and ice, of course, it can tolerate a larger amount of change in temperature to raise its temperature by 1 degree Celsius. This specific heat capacity equal to 420 joule per kilogram degree Celsius, also equal to 1000 kilocalorie per kilogram degree Celsius, and that is equal to, sorry, here is 1 kilogram or kilocalorie per kilogram degree Celsius, and also it equals to 1 calorie over gram degree Celsius. Okay, that's the specific heat capacity of water. Water has an average of 1, equal to 1. Let's show what is above up quiz here. Water has a specific heat capacity of 1 calorie per gram degree Kelvin, and iron has a specific heat capacity of 0.1. If we add the same amount of heat to equal masses of iron and water, which will have the larger change in temperature and why? Think. Of course, it would be the iron, as the water has a higher specific heat capacity than the iron. So, as there is an inverse relation between the change in temperature and the specific heat capacity, the iron will have the larger change in temperature than water. Water can store a larger amount of heat than the iron. Okay, another quiz comparing the amount of heat energy required to raise the temperature of 1 kilogram of water and 1 kilogram of iron. How could we compare that? By substituting in the this relation for water and iron, we can get that it is for water equal to 20,000 calorie, and that of iron is equal to only 2,140. So we can prove that for this quiz that the iron has a larger change in temperature than water. Okay, as shown here is an application for using water as a cool-up factor. Okay, as it has a larger specific heat capacity that it can store a larger amount of heat without changing its temperature. So we can use it in cooling systems for cooling any engines as shown in this figure. Can be a cycle here, circulating the hot water and the cold air can be doing the cooling process. Okay, that passes through these metals into the radiator. Also, in the manufacturing of different substances for cooking, these substances must be made of low specific heat capacity that can tolerate larger amount this source and can tolerate the temperature to increase faster upon heating. We want to decrease the time for foods to be taken a larger time to be rises its temperature. So we uses low metals or cooking utensils with low specific heat capacity than others. Okay, now it's time to know how to measure the specific heat capacity of a known substance using calorimeters. What is the main method that we will use? The first one, which called the mixture method, as we shown in the previous video. The energy lost by the solid object can be equal to the energy gained by the calorimeter in the records. In the shape of the calorimeter, it's an isolated system that isolate the internal heat from the surrounding. Okay, that we can ensure that MC delta T for the lost one equal to negative MC delta T for the gained uh, value for the liquid and container, for the container and liquid. So the mass of the solids times its specific heat capacity times the variation between the specific heat capacity, sorry, the final temperature of the solids and its final temperature for the system. This value equal to MC delta T for water and the container. If this container made from aluminum, that it will begin the temperature, so its temperature would be final temperature would be larger than that of the initial one. So the value we will substitute by multiplying the negative value into the same value as here. We can get that is equal to the final minus the initial value. Okay, but the solid object which has a higher temperature, they can lose energy that if the temperature is larger than that of the total or the final temperature for all the system. Okay, this temperature would be lesser than of the final temperature and larger than that of the initial temperature for the cold system. Okay, let's show how to optimize this using this experiment. The same experiment that I had shown before. Here, this experiment by using the calorimeter, mixture methods as the same way taking the weight of pickles and water, and this is a calorimeter which made from aluminum and electronic balance maker filled with cold water. Okay, the first step then we do we take the mass of the object of the solid object and then putting the calorimeter, the empty calorimeter, and taking its weight by putting the water inside the calorimeter and taking the weight of calorimeter plus water, and so we can get the mass of water only by putting this aluminum container into calorimeter, the isolated system of calorimeter, and taking the internal temperature, and then by heating another water and taking putting it for 2 minutes, then it takes the temperature of the hot object, which is water, to reach about 100 degrees Celsius, and then dropping it this object to take the temperature of the hot water and then putting it into the calorimeter and closing the calorimeter, taking it for a while and recording the temperature, the final temperature as you see here. It's recorded here and then substituting in the relation as shown here. Heat loss equal heat gained by calorimeter and water. Here is the temperature of the hot system, which is 1 degree Celsius minus final temperature, and substituting in this relation to determine the unknown value of the specific value for the unknown aluminum block. Okay, and found this value by joule per kilogram Kelvin dot degree Kelvin. Okay, let's change different metals and test what would be the value of the specific heat capacity for different metals. Here the value of X unknown, which is the unknown value, and here is the value of silver, specific heat capacity of silver, and here we can change the temperature, increase it or decrease, and here is the value of the mass, and we will give the mass of the water and the mass of temperature. Sorry, and the value of the temperature. Is by putting it inside the calorimeter, we found that by increasing the time, the temperature will remain constant until it reaches the maximum value until it will be increases by putting the solid object inside the calculator and taking for a while and recording all the data produced for unknown metals as shown in the figure. By time, there is a variation between the value of the different specific heat capacity according to the different specific heat capacity of different metals. Okay, let's take an example. So if we have 2 liters of water at 20 degrees Celsius mixed with 4 liters of water at 70 degrees Celsius, and supposing no heat transfer as the system is tightly enclosed outside the system, the final temperature of the system would be, by substituting in this relation, C delta T lost equal MC delta 2 T gained. So by substituting for all the values we obtained here, as here is a mass equal 4 and it 4 liters, so we convert this liter into meter cubic. Okay, and then substituting for the initial temperature of the whole system and the initial temperature of the cold system to get the final temperature for the system. As we can conclude that this value is lesser than the hotter object and larger than that of the cold one. Okay. Second method is called the electrical method. By applying an potential difference into two sides of the calorimeters, we can get the same values as obtained for the specific heat capacity. As shown, this would be the figures by putting the voltmeter here to measure the temperatures in parallel, measuring the voltage in parallel, and the meter in series, and then we can get the variations in increasing the temperatures by the variation of the voltage produced. As shown in this relation, is the energy lost by the electric current equal to these values. You have this method. You aren't supposed to understand it or use it as you haven't yet studied electricity in your curriculum, but it is for you to know that we can use another methods for measuring specific heat capacity of any unknown metal. Okay. Second part of our lessons is about specific latent heat.